Hi, everyone. I'm Greg Scontris, Associate Professor of Language Science at the University of California, Irvine, where I direct the Meaning Lab. We're here today for Abralin ao Vivo, Linguists Online. Hi, everyone. An initiative of the Brazilian Linguistics Association. At the University of California, Irvine. And somewhere I'm hearing myself. We're here today for Abralin ao Vivo, Linguists Online. An initiative of the Brazilian Linguistics Association. And somewhere I'm hearing myself. Okay, let me try that again and see if anyone is playing this back. Sounds better. Okay, so Abralin is designed to give students and researchers free access to state-of-the-art discussions on diverse topics related to the study of human language. We have a great talk lined up, and it's a true pleasure to introduce today's speaker, Professor Michael Franke of the University of Osnabrück. Michael is a professor at Osnabrück's Institute for Cognitive Science, where he heads the Cognitive Modeling Group. With degrees in cognitive science, logic, and philosophy, and a habilitation in linguistics, Michael is a true polymath and an authentic intellectual. Broadly, Michael's research applies computational, cognitive, and evolutionary modeling to questions of language use, with a particular focus on pragmatics and semantics, or issues of meaning. When I think of Michael's extensive contributions to the scientific study of linguistic meaning, I think of someone who uses and often develops state-of-the-art methods, applying them to foundational theoretical issues. This approach will be very much on view in today's talk, where Michael will tell us about theory-driven statistical modeling for semantics and pragmatics. I know you'll all join me in welcoming Professor Michael Franke. Keep in mind that you can use the chat function to submit questions as they arise. I'll moderate the discussion at the close of the talk. And now, Michael, thank you for being here, and please feel free to take it away.
Thank you so much, Greg, for the very kind introduction. Thank you very much to all the organizers from Abralin. It's a great pleasure to be here. I hope you can now see my slides. If that is not the case, maybe Greg, tell me. Otherwise, I'll jump right in into theory-driven statistical modeling. So this talk is, like Greg mentioned, heavily methodological. So I would like to start out with a few general remarks on the distinction between theory-driven models and theory-neutral models. If we think of the standard logic of a test-based approach to empirical research, we probably have something in mind like the following. We have a verbal theory. And with verbal theory, I mean not entirely specified as either a mathematical framework or a computer program, but it's not necessarily meant to be something worse than that. It's a theory that's spelled out in language, in ideas. You look at this theory and you ask yourself, which distinguishing features does it have? What predictions of relevance does it make that are surprising, that set that theory off from other theories out there in the market? You think about an experimental design that you could set up that specifically targets this distinguishing feature. Often, these distinguishing features are predictions about a particular difference. The drug has an effect, and you compare a control group to a treatment group. You collect the data and you apply a statistical test, for instance, of difference. Is there really a difference in the measured effect between the control group and the treatment group? And then you interpret the outcome of that statistical test as evidence for or against the hypothesized difference. And then in yet another step, you reflect back on what that means for or against your verbal theory. Now, there's nothing wrong with this approach, absolutely. However, it is probably not the only way in which you can do empirical research. One thing to notice about this kind of approach is that it assumes, or it often assumes, that the statistics that we're using are off the shelf. And with that, I mean that they can equally be applied in psycholinguistics, in biology, in physics, and also in sociology, for instance. And in this sense, the standard tests that we use, regression modeling, t-tests, ANOVA, and what you have, are theory neutral. They are meant to be generally applicable, but therefore they don't necessarily directly, I mean, they could, but usually they don't, connect to the kind of special domain theory that you are trying to test. However, if you take a model-centric approach to statistics, which is basically nothing new, any statistical test that you learn in your Stats 101 has an underlying model theoretic formulation, you could say. You can start to play around much more freely with integrating theory into statistical models. So more concretely, a statistical model often has, very broadly speaking, the following structure. You have some parameters, if it's a parametric test, otherwise maybe not, which feed into some kind of predicted value, what you would expect on average to happen, from which you derive a likelihood function over potential outcomes, and you link that to the data. So the first parts in this model-centric approach here, the parameters and the predictor, you could say, are the analysts' assumptions about the data generating process. And this could be, for instance, just some linear predictor, like in linear regression model. But it could also be any kind of linguistic theory that drives the likelihood and that drives the explanation of your data all the way from theory to data. And so this talk is going to be about exploring this symbiosis of statistical and cognitive modeling from the point of view of linguistic theory. I should say that what I'm saying here about model-centric statistics and doing more theory-driven statistical modeling is not new. Many people are arguing for similar things in other disciplines. However, I think that in particular, if you look at the recent empirical turn, so to speak, in semantics and pragmatics, where we have a very strong established linguistic theory, interesting honed terminology and established theories, we now turn to experiments and we want to test these established theoretical ideas. So we are in a position, in a sense, where it is particularly prominent or maybe even pressing to try to link directly what we think of are interesting theoretical constructs to what we can observe in an experiment. So my agenda for this talk today is to introduce ideas of probabilistic modeling as a kind of scaffolding to test established theoretical ideas from linguistics, in particular from semantics and pragmatics, based on experimental data. And in order to do that, I want to take you rather swiftly through 3 case studies. First one on grammatically generated implicature readings. Second one on gradients in locality and natural language quantification. And then the last one is an outlook on task-type link functions and what is actually measured by experimental task. A word of caution, all of these case studies could be dealt with in a 1-hour talk or even longer. So I will have to cut many corners. I would like this talk to be generally interesting also to people who are not familiar with, let's say, probabilistic modeling and even some of the semantic/pragmatic theory that I'll be touching. So please keep in mind, I will, first of all, skip some very interesting detail because we don't have time for it. And second of all, just try to keep track of the overall red thread through this talk, which is how you can use explicit mathematical / computational modeling to link theory, statistics, and data. Let's go. First case study. This case study is based on joint work from a recent paper that appeared in Language last year with Leon Bergen. And it deals with grammatically generated implicature readings. Let me first illustrate what the topic of the case study is. So I'm assuming as linguists, you are reasonably familiar with scalar inferences. Usually we say that from an utterance of a sentence like 1A, I own some of Johnny Cash's albums, we're inclined to infer 1B that I own some but not all of them. The standard explanation is because otherwise I could probably have said 1C, I own all of Johnny Cash's albums. Now, a traditional explanation of these kinds of scalar implicatures is that they fall out of a rationalization of the speaker's utterance in a context. Just like I did just now, I said, speaker didn't say that they owned all of Johnny Cash's albums. So probably it's not the case that they do. However, already from the start of original Gricean ideas of pragmatic reasoning, people have noted that this picture has some problems explaining certain inferences that seem to occur in embedded positions. And so very recently, a very interesting research program, which I'll here call Grammaticalism, has been proposed, which basically suggests that a grammatical mechanism in the semantics is responsible for generating candidate scalar implicature readings. So let's have a closer look at what that would mean. So here are complex sentences, or actually it's just one complex sentence. We'll see more of those in a moment, and its potential readings. Take a sentence like 2A. All of the aliens drank some of their water. On a literal reading, key term to look for is obviously quantifier some. This sentence just means that all of the aliens drank some and maybe all of their water. It's just the literal reading. However, we can, by standard Gricean reasoning, contrast this sentence, the 2A, with a stronger sentence like all of the aliens drank all of their water, and say, okay, the speaker didn't say that stronger sentence, so we'll read this first sentence 2A as 2C, the global reading. All of the aliens drank some of their water, and it is not the case that all drank all of it. However, it is also plausible that there is another stronger sentence than 2A, or a reading of 2A, which is the one in 2D, the so-called local reading. All of the aliens drank some but not all of their water, where you could say that pragmatics, so to speak, the enrichment of some happens inside the scope of a logical operator like all. And we could say that what grammaticalism does, it supplies this reading, so to speak, and we'll see how it does that in a moment. And the empirical question is obviously, do we need it? And this is the part of what I would like to contribute to today. So if we think about grammatically generated implicature readings of sentences of the following kind, outer quantifier of the aliens drank inner quantifier of their water, with an alleged very simplified syntactic structure of the following variety, then grammaticalism would tell us that there are different parses / readings supplied by grammar, syntax, semantics interface in such a way that an exhaustive operator whose meaning is roughly equivalent to that of an overt only can apply at matrix position at the whole sentence level. It can apply at the inner quantifier, and it can also apply or not apply at the outer quantifier. So if an exhaustivity operator would, for instance, apply locally to a noun phrase some of their water, it would get enriched to mean some but not all of their water, and so on. At the matrix level, the exhaustive operator would be give or take, equivalent to standard globalist Gricean reasoning, negating stronger sentences, complete sentences. So this may already be quite a lot of detail. Let's take a step back. What does that mean? We have a theory that is empirically well motivated, that suggests that hidden operators that generate candidate pragmatic readings can apply at different scope size. For simple sentences like the ones I suggest here with 2 potential logical quantifiers, there are then 8 possible parsers or 8 possible readings that you can obtain by inserting or not inserting these exhaustive operators at these 3 different scope sites. We get a literal parse where no exhaustive operator applies. We get a reading where only we have only one at the outer position. Only at the matrix position, only at the outer position, only at the inner position, and maybe at several scope sites conjointly. A traditional Gricean approach would only acknowledge, in a sense, the literal reading without any exhaust, like it's just a semantic reading, or the one that you can obtain by global Gricean reasoning, which we here can approximate by saying, okay, apply exhaustification at the matrix level. Whereas a grammatical approach would, in principle, allow for all of those potential readings to be derivable, to be available for the interpreter. Now, of course, depending on what these quantifiers are, and also depending on what version of exhaust you might use, some of these readings might be equivalent to other readings, but we'll see that in a moment. Okay. The question that I'm interested in here is, again, to ask how much of that ambiguity, so to speak, do we actually have empirical evidence for? And as you can guess by the whole introduction to the talk, you will use probabilistic pragmatic modeling to try to answer that question, or to try to give a partial answer to that question. So let's first have a look at experimental data that we can work with. The experimental data from the paper that I'm presenting here looked at 9 sentences, and I'll call them nested Aristotelians because they are basically of the structure that we just looked at: outer quantifier of the alien's drank, inner quantifier of their water, where the quantifiers are all the Aristotelian lexicalized quantifiers, all, some, and none, with all possible combinations. The abbreviations I'll use in some of the figures that you will see are, for instance, AN for all, A of the alien's drank, none of their water, N, and so on. Based on the standard logical meaning of these sentences, we can distinguish 7 world states, also including potential pragmatic enrichments. So there's only 7 distinct states of the world that we can distinguish with this miniature language. These are stimuli from our experiment, and these are the states, the world states that we'll use to probe participants' interpretation and production behavior. So you see a bunch of happy aliens here, and each one has a jar of water, and they have either not drunk anything, like these guys, or they emptied all of their jars, like these guys, or some drank nothing, some drank half of it, and some drank all of it. So we can represent those 7 world states if you're interested, but you don't necessarily have to follow that notation. For instance, with this miniature icon here that says there is no, in this situation, there is no alien that drank all of the water. There are aliens that drank half, and there's no alien that drank nothing. Just to use these icons succinctly in visual representations of the results, for instance. But I'll talk you through the critical ones, and it's not going to be important. So with this material, we recruited 100 participants using Amazon's Mechanical Turk. Only self-reported native speakers of English were allowed. We presented them with a cover story about scientific research on, obviously, friendly scientific research with friendly aliens who came to Earth, and we were just interested in what they like to drink. The materials, as I said, consisted of these 9 nested Aristotelians, and we presented the 7 possible will states with pictures like the ones you just saw in T again. The experiment had 2 parts. Each participant first went through a task series that I will refer to as production. Proviso will be coming in a moment, whether it's true production or not, and a comprehension task. Okay, let's have a look at the production trials. In what I will call production trial, somewhat sloppily, participants were presented with a display of a will state and got the instruction, please describe the situation for the scientist as best as you can. And the production consisted in selecting from 2 drop-down menus an Aristotelian quantifier at each position. So that is, in a sense, a very confined way of asking, how would you describe this picture given the 9 Aristotelians? In what I call comprehension trials, participants were shown a similar picture, or actually shown all 7 pictures of will states, together with a given statement, like none of the monsters drank some of their water. And the question, how likely do you think that someone else had this situation in mind when they uttered this sentence? Right? And they had to rate this with a slider for each of the 7 possible will states. So what is the data that came out of here? I'm just going to throw it at you. The production data and the interpretation data. Don't worry, we're not going to dig too deeply into this. We'll just use the data en bloc for modeling purposes. I just want to show you for once that there is data and how it roughly looked like. So in production, for each situation that you see here, let's say along the vertical line, we'll get some proportion of times that people chose, so to speak, a nested Aristotelian. So here's a situation where all of the aliens actually drank half of their water. And the preferred way of saying this or expressing this, describing this will state, is by choosing the nested Aristotelian. All of the aliens drank some of their water, unsurprisingly. Reversely, if in interpretation participants heard the sentence, all of the aliens drank some of their water, they rated with sliders for each of these situations how likely they thought. We normalized their ratings for all 7 sliders and then averaged. And this is what you see here. So according to this measure, the most likely interpretation, according to our participants, is, again, this state where all aliens drank some, but not all of their water. So you could say a local reading is the most preferred reading according to this measure. But what does that mean for any other type of reading that could be generated by inserting hidden exhaustive operators for all of the other sentences in place? And that is the question that I'm trying to address here now with pragmatic modeling, probabilistic pragmatic modeling. We will use a particular way of probabilistic pragmatic modeling in the following. So I'll take a step back here now and introduce this once for all of the 3 case studies that we're going to look at. Essentially, what I'm endorsing here is a theory roughly like the rational speech act model introduced by Noah Goodman and Michael Franke. Take the position of a pragmatic interpreter. What's the job of a pragmatic interpreter? A pragmatic interpreter hears an actual speaker uttering some observable message. Let's say very simply just bike. That speaker has in his mind some kind of meaning that they would like to convey, but that pragmatic interpreter cannot observe the meaning. They can only observe the extensive signal like bike. So their job, you could say, or what they might have to do, is come up with interpretation hypotheses. What could the speaker have meant with bike? Was it a motorbike? Was it a race bike? Or was it a regular bike? And weigh those interpretation alternatives according to how plausible they think these are. And according to the framework I'm adopting here, the way in which these alternative hypotheses are ranked or weighted against each other is by simulating a model of the speaker's behavior, essentially asking if the speaker had wanted to express, let's say, motorbike, what would the speaker have said? How likely is it that he would have said bike? Would he not have used an alternative expression? Doing this all probabilistically, then we'll arrive at something like an abductive inference or a rationalization of the speaker's utterance by reasoning towards the best explanation. So the most likely state that would have triggered the message that we have observed. In full-fledged models that apply this kind of reasoning framework, we would also like to look at the pragmatic interpreter's knowledge of language, but also the reasoning about knowledge of language of the speaker, which is important for our first application. In other applications, we might also want to include reasoning about general shared world knowledge on the side of the interpreter or over what the interpreter thinks the speaker has in mind. And finally, obviously also about more specific parameters of the concrete context that we are engaged in. However, these last two bits do not play a major role for the case studies that I'm looking at. In order to formalize these ideas, the Vanilla Rational Speech Act model formulates essentially two conditional probabilities, which I'll call a speaker rule and a listener rule. So a speaker rule is a conditional probability distribution that assigns a probability to an utterance given a state. And a listener rule is, in a sense, the reverse. Given an utterance, how likely is it that that the speaker had a particular state interpretation in mind? The model assumes that the speaker rule is grounded out in literal interpretation, so to speak. So an utterance comes with a semantic meaning indicated here by these double denotation brackets. And a speaker is trying to choose an utterance for a given world state such that under a literal interpretation, this here, conditional on a literal interpretation, the probability of inferring the world state is as high as possible, modulo some parameter that can be tweaked to model more or less informative speakers. The idea behind this formulation is that the speaker is trying to make an assumed literal interpreter, who interprets literally, infer the true state with as high a probability as possible. Under some defensible assumptions, this formulation can also be rewritten in a more standard way, recognizable to people familiar with Gricean pragmatics, namely that the speaker is trying to adhere to truth of what they say and also trying to optimize the informativity of a message, which is just maybe measured in terms of the numbers of states, relevant world states that are true of it. So the Gricean interpreter, on the other hand, basically, like I said previously, would reverse this whole process and prefer an interpretation that makes it likely that the speaker would choose the utterance that they had actually observed. So that is the general probabilistic pragmatics modeling scheme that I'll be endorsing for actually all of the three case studies with some variations that are going to follow. Back to the concrete one that we looked at. So far, in this vanilla RSA model, there was no mentioning of the semantic ambiguity introduced by the grammatical approach. And so there's very little we can say about the data that we just looked at from our little experiment. In a way, you could look at it in this way, that we have the potential parsers suggested by grammaticalism. And the vanilla rational speech act model, if we don't do anything to it, would only assume that the semantics of an expression is its logical, its literal semantics. However, we can start giving up this assumption. We can give up this assumption and just include more of the semantically generated ambiguity into our model. A first attempt of doing this has been given by Chris Potts and colleagues in what they and I call the lexical uncertainty model. Without going into detail, the lexical uncertainty model assumes that there are literal readings available for our nested Aristotelians, and that some can also mean some but not all. But a speaker who has a lexical meaning incorporated in their head that some means some but not all will use some always to mean some but not all. So the only parse that's also available to these speakers is a parse where we have a local exhaustification at both embedded scope sites. We can generalize this slightly more, and we could say, okay, now maybe we want to have more flexible speakers that can use some once in a sentence to mean some but not all, and use another occurrence of some to mean some and maybe all. So these speakers would have two more potential readings available to them, and they could use them in some sense. And we call that the lexical intensions model. Intentions because the way it is formalized in these models is that the speaker actually chooses a sentence with a specific meaning of each occurrence of each quantifier in mind. We can even generalize this further and look at a global intentions model, which is similar to the lexical intentions model, but allows for the full variety of parses made available by grammaticalism. Okay, that's a lot to take in. Last slide on these formalisms, just to give you an idea of how this global intentions model would look like. Essentially, it looks very much like the vanilla rational speech act model that I've just introduced, but it adds one parameter, P. And P is a parse, one of the 8 parses that we just saw in the rows on the table before. So the speaker is now assumed for a given meaning that they want to express to choose an utterance and also to choose a parse. What that means is, let's say I say all of the aliens drank some of their water, and in the back of my mind, which you can't see, I intend that sentence to be read as the meaning that comes out if you apply the parse P. And you, as a speaker, as a listener, you don't know that P, you only heard the utterance U, but you can jointly reason about which pair of actual world state and speaker intended reading of the sentence best rationalizes the fact that the speaker just said all of the aliens drank some of their water. Okay, so with these models in place, we can turn back to our experimental data. And now, of course, we have to skip a few technical details, but basically what we do is we use Bayesian model comparison to ask the question of a rational scientist, how credible is each model given the data? I'll give you a brief overview of how this would look like. The basic architecture of all of the 4 models that we just saw is roughly this. We have 2 parameters. There's this alpha that you actually saw, the rationality parameter. In the actual modeling in this paper, there's another parameter, namely the cost of negative utterances. But let's put that aside. These are 3 parameters of the model, just like you have 3 parameters, let's say, in a regression model. Both of these parameters influence the predictions of the speaker rule and the listener rule. They feed into both. The speaker rule, the probability of an utterance given a state, is directly what explains or could explain the data from the production data. It provides a likelihood function for the data from this production task that we had. Similarly, the listener rule almost directly provides a likelihood function for the interpretation part of the data. So the likelihood for all of the data combined, production and interpretation at the same time, is just the product of those 2. And we can say for each model, given an average over all possible parameter values, which we'll just set as an interval over in principal plausible ranges, how likely is the observed data given that model? And when we have such a likelihood term, which is really simple to compute, we can turn that around and ask the question that we're really interested in. Namely, given the data, how likely, relative to all the other models, is a particular model from the set of these four? That's easy to compute, actually really rather straightforward to compute, given that we have rather simple models with just 2 free parameters. And the resulting numbers are extremely intuitive to interpret. So the posterior probability of models given the data, on the assumption that all of our modeling, that there are really only those 4 models, so it's always relative to the very narrow focus on the models that we look at, we'll find that the global intentions model is leagues more likely than the second best model. Leagues means here 27 times more likely than this, and that's quite a lot, which in turn is more than 30% more likely than the lexical uncertainty model, and the vanilla RSA model is comparatively completely negligible. So what that means is, first of all, we have used probabilistic pragmatic modeling to squeeze quantitative predictions from grammaticalism. Grammaticalism, as I introduced it, there are papers who try to constrain the set of potential readings more further. That's for granted. But grammaticalism, as I introduced it, just said there are many available readings. Couching grammaticalism inside of probabilistic pragmatics, however, allowed us to derive quantitative predictions for a model that contained so and so many grammatical readings, so to speak. The result of this exercise was that it seems that we need the full range of implicature readings that are generated by grammaticalism, which is a directly interpretable, theoretically meaningful result that is not derived by deriving a, let's say, point hypothesis about a comparison between groups or something like that, but taking the whole data into account, both from production and from comprehension. All right, let's see if we can still stomach a second case study. This one is joint work with Bob van Thiel and Uli Sauerland in a paper from this year, and it's dealing with gradients and focality in natural language quantification. We've already talked about quantifiers a lot, just for setting the scene again. Now we're going to talk about more quantifiers than just the Aristotelian ones. That's a relief, probably. Stuff like some of Billy Pilgrim's memories are pleasant, so some reoccurs probably. Gideon's backhand smashed exactly 3 skeletons, or Seymour spotted many banana fish. All of the orange ones being quantifiers that we now possibly care about. Semantic theory tells us, one prominent semantic theory tells us that the truth conditions that for the meaning of a sentence like Q, quantifier, of the S, some property, or P, another property, is a function of the intersection set size. So the cardinality of the intersection between those predicates in question. So as, for instance, a sentence like sum of the SRP just means that the ISS is bigger than 0. And this also can work for context variable quantifiers like many. Then you just have to say that there's some threshold that is supplied by the context against which you compare the intersection set size, for instance. This is a really good and powerful theory because it offers very interesting, formally precise notions such as monotonicity, which can then help explain a lot of puzzling observations from several domains, like the cognitive complexity of quantity concepts, stages in the acquisition of quantity words, the amount of errors that people make in certain reasoning tasks, and also for theoretical purposes, the distribution of polarity items at least has been suggested to also be influenced by monotonicity. However, If we look at empirical data from quantifiers in use, we'll see a slightly different picture from what generalized quantifier theory would suggest. Data that is already rather old, from the 70s, for instance, has shown that if you ask people for their preferred interpretations for various quantity words, like a few, several, and some, that seems to deviate quite from the logical meaning. Let's zoom in again on the word some, just because it's so familiar for us. Then, according to generalized quantifier theory, the logical meaning in light green is something like, well, just more than 0, at least 1, or maybe at least 2, depending if you want to say some plural presupposition or something like that. It's not important for us. But anything bigger than 2 is certainly true. However, if we look at the typical ranges of interpretation, that's the dark green one, they are much more narrowly confined. And that is the kind of focality, and as you will see in a moment, also the gradients that I would like to address in this talk. So again, let's look at an experiment that gives us something to work with. Here, we're looking not at interpretation, but at production, and now in a more open-ended set. A simple experiment invited in total 800 participants, 600 of which consisted of the training set, or give us the training data, and 200 of which give us the test data, to perform an online experiments at Amazon's Mechanical Turk. They saw pictures with 432 dots, like this one here, varying proportions of which were red, the rest black. And they saw this trial like that, and could freely type a quantifying expressions to complete this sentence of the circles are red. Participants were kindly asked not to produce numeric, like explicitly numeric expressions like 30%, for instance. They still did, so we filtered that out. But for the most part, this elicited quantifier expressions just like many, most, about half, etc. In particular, we now look at just the 15 most frequently produced types, not tokens. So after classifying certain near equivalents and some spelling errors into the same categories, we are left with 15 most frequent quantifiers. And we also look at all or none. All or none weren't produced very often. But that is just an artifact of the situations in which they would be true, not being shown very often. So in order to have those edge cases included for modeling, we also include all or none. And what we see here along the x-axis is the number of red circles that participants saw in our experiment, together with a smoothed out density estimation of how likely particular quantifiers would be used in these cases to describe that scene. And again, what we see is, let's say, not what you would expect from generalized quantifier theory, which assumes that there is some threshold, and after that, that expression might be true, or up to that, the expression might be true. But maybe rather something, if you just eyeball this data, that is accountable by some kind of prototype-based theory, where we would say, like, very maybe prominently here, half has a prototype that is exactly in the middle. It actually isn't here, at least not the top one. But it has some kind of prototype, and the region of use, or the use of these quantifiers, is maybe described by something that has a prototype and some distance function from the prototype, according to which that is still this expression is still applicable. And indeed, some people have argued for prototype-based semantics of quantifiers. But that is tricky, because how do you actually test for which semantics is best? Okay, again, we could maybe try to devise an experiment that sets up a particular condition in which generalized quantifier theory would predict this, and prototype theory would predict that. But let's take the data as we have it and try to infer backwards what that data means about the contrast between a classical binary generalized quantifier theoretic semantics and a potential prototype-based semantics. And this is what we do with probabilistic models of quantifier use. Here, I'll skip a lot of the details, actually. So I'll just keep it at the basic architecture of the models in question. We have the data from the production study that I just mentioned. We want to derive, similarly as to what we had before, a speaker rule, which I call the production probability of the speaker, choosing a quantifying expression given a world state, which is here labeled T, in particular T prime. The hidden moving parts, the parameters, so to speak, that affect this production probability are, again, speaker's rationality parameter, not a cost this time, but rather a salience. There's a subtle difference between cost and salience, something you might ask for in the Q&A. Otherwise, think of it as roughly the same as the cost that we had before. But then two additional components, namely the lexicon and the ANS component. So the lexicon is, depending on the type of model we have, of which we have four, either generalized quantifier theory or prototype theory. And we are using the data to backwards infer through this pragmatic link function what a likely semantic meaning could be for a given quantifier. But we do it in the way that one model exclusively assumes generalized quantifier theoretic semantics, and another model assumes exclusively prototype theoretic semantic meaning. We'll also distinguish pragmatic speakers from just literal speakers, because prototype theoretic semantics, in a sense, already could be said to incorporate pragmatic reasoning, excluding other states that could better be expressed by a different quantifier. So in order to be fair, we also look at just literal language users, because that might be fairer to a prototype theoretic semantic explanation. Lastly, this model also has an ANS component. ANS for approximate number system, and the general idea is that given a true state T, the true number of red dots, for instance, in a display might not be known to the participants, who were also instructed to not try to count all those 432 dots, but they might just have a vague percept of the actual state. So we'll define a noisy probabilistic function from true state to perceived state, and we'll say that what the speaker actually chooses a quantifier to is their possibly noisy percept of the true world state. Details have to be skipped for the purpose of this talk, unfortunately. So I'll skip those. So for those four models that we just had, we can again do Bayesian model comparison, asking the same question: which model should we believe in? We do it slightly different here for technical reasons. So we're not using posterior probabilities. We'll use, we look at posterior predictive distributions, and we'll, on the next slide, look at cross-validation results. If you're interested in the differences, bring it up in the Q&A. So once more, what we had for this experiment in the training data, it's the same data as we saw before, but in a different format of representation. And we had test data. So what we do, similarly to what you often see in computational linguistics or in machine learning, is we use this training data to basically train our models, in this case, to compute posterior values over credible parameters, because there's a lot of parameters in these models, because we have one or sometimes two parameters for each of these quantifiers, for instance, and we have a salience value once for almost all of these quantity expressions. And what you see down here is the predictions a trained model of a particular kind would make based on this data. And what you can see, for instance, is that a literal speaker who uses generalized quantifier theory is perceptibly different from all the other ones. For instance, in the case of most, which is this piglet pink kind of color here, they would continue, so to speak, to use most rather prominently as the number of red dots, for instance, would grow towards the total number of 432. Whereas pragmatic speakers and also literal speakers using a prototype theoretic semantics would decrease the frequency with which they produce most. However, not particularly clear how to distinguish those with the naked eye. So that's why we now turn to the test data set and we'll ask, for those trained models, how likely is the test data, the holdout data set? And the log likelihood of the test data is plotted here. So we meant the higher, the better. So how likely is the holdout data set given the trained models? Gerade nicht. The neighbor. Pragmatic generalized quantifier theory provides the best score on this account by a margin. To test this even further, very briefly, we also looked at empirical model comparison. That is, we invited another 200 experiments into our virtual lab via mTurk, so to speak. And we showed them the same displays. And we randomly sampled a prediction, so to speak, from one of the 4 models. And also we sampled what other participants had actually said in the data for that picture. And then we had them rate with a slider whether that particular description was good or bad. And so we can compare the posterior predictions from an empirical point of view, also against the actual data. The results are that a literal speaker with generalized quantifier theoretic semantics is really worse than everyone else. But there's no statistically significant difference between these empirical measures for all of the other 3 models. So here, the pragmatic model, which uses generalized quantifier theory, is not necessarily the best one. It's also not worse, but we can't say, which is okay for us. Because what we would like to conclude from this is rather that, first of all, gradients and focality that we see in the data seems to be consistent with generalized quantifier theory. Generalized quantifier theory is not necessarily ruled out by just seeing focal areas that flow into one another, so to speak. But the more important methodological point I would like to make here is that we can test semantic theories through the lens of a pragmatic link model. So we can use the pragmatic model to draw theoretically interesting conclusions about latent moving parts that we cannot directly observe, that we can only study through their reflexes. And the pragmatic link model makes those reflexes, this stream that we imagine of going from the latent structure to the data, maximally explicit. And that's a good thing. Last one, shorter. Case study 3, task types, link functions, and what is measured. Let's start with the experiment immediately. So suppose you see this, some of the circles are black. You see a display, one black circle, and you are asked, is the sentence true or false in this picture? The experiment only lets you press on one button, make up your mind whatever you would want to say. Now imagine different type of task, different experiments, same picture, same sentence. But the question is not about truth and falsity, but how well does the sentence describe the picture? And you can choose from 7 categories on a Likert scale from bad to good. What would you do? And we ran this kind of experiment. based on a particular variation. So first of all, I varied the type of task, 7-point rating scale with the question, how well does the sentence describe the picture? And binary truth value judgment, is the sentence true or false in this picture, just as shown now. Then there's cross classification. In half of the experiments, between participants manipulation, there were filler sentences with most and many, and in the other half there were not. They just these participants never saw most and many. The specific theoretical reasons for doing this are not so important. I want to make a methodological point. Here's the data from this experiment. On the x-axis, you see the condition, how many of the balls are actually black, 0 to 10. And for the Likert scale, you see here the mean ratings rescaled to lie between 0 and 1 for comparability. Once for the case where many and most were absent in gray, and for when they were present. And for the binary truth value judgment task, what you see here is the proportion of truth judgments for all of these cases. And what you see here, similarly for absent and present alternatives. Now I want to introduce a straw man interpreter here, which I'm going to bash on. And that person would reason as follows. Obviously, the binary measure, if we ask for truth conditions, measures the truth conditions of the sentence. Obviously, if you ask for how well does the sentence describe the picture and you give the 7-point rating scale, you're measuring something else. You're measuring pragmatic felicity. And you can see that in the data because truth conditions are unaffected by adding alternatives, many and most, obviously, because truth, But pragmatic felicity is affected by adding other alternatives. Now, this is a straw man position, and it's over-exaggerating this, but maybe if you have read experimental semantics and pragmatics papers, you sometimes have felt that, aren't we over-interpreting subtleties in the results with respect to how they relate to theoretical notions such as truth conditions and pragmatic felicity? So I think, again, here, explicit probabilistic modeling can help. And here the model is not broken down. That's the full representation of the full model, but don't despair. I'll talk you through it. What I want to do here is I want to look at the data. The data from the Likert scale on the one side, the data from the truth conditional binary truth condition truth or judgment task on the other side. We'll have two variants of all of that, ones with the alternatives and ones without, but that's not so very important. More important is that the data is obviously explained by a latent structure, the last layer of which is again the likelihood function, the choice probabilities of choosing one of the degrees on the Likert scale or choosing true or false in the task for everything else, like with or without many and most present in the experiment. How do we generate those choice probabilities? Well, for the binary judgments, we'll just look at standard logistic regression models and use their logistic linking function. For ordinal data, Likert scale rating data, we also just use what you would use in ordinal regression, here in particular, a probit linking function. And the input, and that's the important bit, to those standard linking function for the type of data that we collected is a theoretically informed notion of pragmatic felicity. So we are assuming, that's the most important thing, we're assuming that both tasks measure pragmatic felicity. Pragmatic felicity has a formal derivation in terms of RSA, in terms of probabilistic pragmatics, but for our purposes, we can just take it as it measures how good the description sum is as a description of the given picture. And then we can look, this is just one model. Remember, all the other case studies so far had different models and we compared them. This is just one model. And the model assumes the tasks measure the very same thing. So we train the model, so to speak, on the data, and then we compare what the trained model would predict about any future data. That's a so-called posterior predictive check, in particular here, a visual posterior predictive check. And the logic behind that is the trained model surprised by the data it was trained on, right? And it's not. You see that by the model predictions in red and 95% credible ranges over these posterior predictions, always including the data that was seen. What that means is that a 7-point felicity task and a binary truth value judgment task may actually measure the same thing. So it's like an existence argument. Look, here is a model that assumes they measure the same thing, and it's doing completely all right. The main methodological point, which is even more important than the specific one, of course, is that using a fully spelled out probabilistic model of this kind has the potential of pointing out to us exactly what we as modelists believe a particular task measures. Pragmatic felicity. It was an ingredient in this tree-like depiction of the model. So we can make very explicit what we believe is measured by a task, and I think that's a very good thing. So I'm concluding here, in general, that I think there is added value to model-centric, in particular theory-driven statistical modeling. And maybe now it's also more clear why I contrasted earlier on the regression coefficient, like the regression predictor, to one of linguistic theory, because that's exactly what we did in the last case study, where we did not derive the input to an ordinal or logistic link function as we would normally do from a linear predictor in a regression model, but from a linguistic theoretically informed concept. All right, thank you very much for your attention. I'm looking forward to your questions.
Thank you so much, Michal. So now we'll transition into the discussion, and let me remind those of you out there watching that you can use the chat function to ask any questions, and I'll monitor the chat and read those aloud. Okay, so as you think of your questions, I have a couple of questions for you, Michal, that I thought we could start off with. One is a more practical one. So assuming that you're a linguist who wants to be able to apply these methods, most linguistic training doesn't teach you these things. And there are only so many hours in a day. What sort of training or background do you need? How can you go about acquiring it?
This is an excellent question. So first of all, I don't think that's very important that everybody should do this or has to do this. That should be very clear, right? So there should be no shame in not doing it. Ideally, however, we are all aware that there is this approach and that we see its advantages and also its disadvantages. If you want to learn this kind of modeling, I think, let's say from scratch, I think learning statistics in general in a model-based fashion is the best thing to do anyway. So maybe that's not what you might have expected, but if you take a statistics class as an undergraduate linguistics student or cognitive science student or something in this vicinity, and you have a chance to take a course that focuses on models and not tests, I recommend going for the model-based course, because it tells you that statistical methods are more flexible than just applying the appropriate test from some arcane decision tree that tells you what test you might need. And once you are comfortable with, let's say, standard statistical models, like a linear regression model, and maybe then a generalized linear regression model, and you know how they are trained and how they're applied, how different models are compared, it's not much further to changing crucial things in the model that make them theory specific. Of course, then the question is, how do you implement that? But also there, I would say, if you are familiar with a standard programming language like Python or R or Julia, there are very good packages that make slight changes to particular models already rather doable. And other than that, I think there's really great also textbooks and courses that could bring you into, let's say, probabilistic cognitive modeling. I would like to mention a textbook by Michael D. Lee and Jan-Erik Wagenmakers, Erik-Jan Wagenmakers, I'm sorry, which I think is very excellent. It takes you step by step through exercises into building your own data analytic models and later cognitive models.
Okay, great. Thank you for that. Another question that I had about linking hypotheses. So I think you've convinced us that we need linking hypotheses to map between the data that we're observing, the behavior that we're observing, and the cognitive processes that we think are generating those data. And I think most linguists, whether they acknowledge it or not, tacitly assume linking hypotheses. What I'm wondering is whether we need computational models for those linking hypotheses. Is it ever the case that some prose level description of that hypothesis is going to be enough? Can we get away with qualitative predictions?
Yes, I think that's an excellent question. And I think the answer is always positive. I think it is being explicit about your assumptions is always good, but it has to be being as explicit as you can. And sometimes we might just want to be able to do something, and that is completely fine, without being able to spell out everything. And is it then a shame to do it? No, it's not. I really don't think it is. I think, for instance, if you look at interpretation of neurological data, EEG data, we are coming to a better and better understanding of what the N400 component, for instance, tells us in language understanding. There are models. There's also controversy about which model is correct and they're specific. And these models are partly fully formalized, but not to the extent I think that they would, at least not according to my current knowledge, that they would derive a very concrete likelihood function to apply directly to the raw data or the pre-processed data. Is that bad? No, not at all. Not at all. The moment where you might need everything to be spelled out, including your link function, is presumably when you want to start comparing the whole data and not just the chunk that you've carved out because it's more according to the modeler's intuition or good arguments is the most relevant one. So suppose I look again at the nested Aristotelians, I could just focus on the predictions for one sentence or two, because that's where I'm assuming the local reading, all of the aliens drank some, but not all of them, water, shows its face most clearly, and that's fine. But if you stick with this kind of case study, the first one and this modeling, then there are potential pragmatic readings for all other or many other kinds of sentences, and your theory should somehow also say something about all of these cases, and then it gets very tricky to do that in a not fully formalized or computational way. So as soon as you want to compare an idea based on its predictions for more than 1, 2, 3 clear-cut cases, but let's say all the data from the big experiment, I think going computational is just necessary because of the otherwise implied complexity. And also for being able to weigh how, let's say in one condition, the data speaks for that model, in another condition, it speaks for the other, and so on. How do you weigh that in? And that is where full-fledged statistical modeling can help. It often, of course, can give you a quite different picture from just focusing on one condition when you basically integrate over all the data that you have. But I think that's really where I would say from the top of my head, that's the clearest case where you want to go computational.
Okay, thank you. Yeah, so I totally agree on the, so it seems like there are 2 points. One, there could be so much data, so many predictions, or it's just so complex that you're going to start spinning in circles if you don't have a more powerful way of specifying the predictions, but also it forces you to be maximally explicit about the assumptions that you're making in specifying a computational model. And I think those of us who have done that have often come across cases where we're surprised by the assumptions that we had been making, or seeing them in front of us, it can be more illuminating. I'm wondering though, why probabilistic? Do these things need to be probabilistic? Are the processes, are the cognitive processes probabilistic? Is it the methods that's introducing the gradients? You touched on this a little bit in the last case study, but I was hoping you could say a little bit more.
Yeah. If not probabilistic, then what? You could ask cheekily back, right? But I think the strongest argument, and the one that I would also really like to defend, is that it's instrumental. It's an instrumental choice. It's the best we have. However, I want to be clear. These models that I introduced are probabilistic at many levels. They are probabilistic at the level of the likelihood with some noise, and so that where you could say this is statistics, this is objective noise, or you could say something like that. But then there's also the subjective part, or the allegedly cognitively real probabilistic part, where we say the choice rules, the speaker rule and the listener rule, are also probabilistic. So yeah, I think you have to keep these separate. However, for both cases, I think it's fine to say there is a clear asset for using probabilities. They're actually rather simple. We know a lot about them. We know how to compute with them. They have a lot of nice mathematical properties, and maybe not so nice mathematical properties, but we know how to integrate the probabilistic cognitive models with the with a probabilistic link function. And we can write them down in the same software package, and it works, like more or less. So I think that's a strong instrumentalist point. For instance, if you think about representations of uncertainty in humans, like higher level uncertainty or actually reasoning with uncertainty, there's a lot of evidence that suggests that human reasoners are not actually very good at applying Bayes' rule, applying general probabilistic reasoning, although you can always look more carefully and look at why they might not be so good at this. But there might be reasons for, at least in certain cases, assuming some more elaborate structure for representing uncertainty of an agent, like Dempster-Schaffner functions. But how do you calculate with them? How do you integrate them into your cognitive model? And like you just said mentioned in your first question, also the probabilistic modeling is already quite a step maybe for linguists, for undergraduate linguists. So I think sticking with probabilities and using tools in your favorite programming language that allows you to compute with probabilities is a good advice. But that doesn't necessarily mean that one has to not be critical about using probabilities, I think, especially in the cognitive modeling part.
So if I have a probabilistic cognitive model, does that necessarily mean that I'm hypothesizing that there are aspects of the grammar that are probabilistic? It seemed like you dug into this a little bit with the case study inferring quantifier meaning, looking at GQT versus prototype theory. It seems like whether or not this is a good thing, linguists are generally resistant to, or at least some linguists are resistant to, assuming that aspects of grammar are probabilistic. What is your view on the role of probabilities in grammar when we're assuming them in the cognitive models?
That's, again, in grammar can mean a lot of things. In the quantifier study, if I may stick first to what I feel more confident about, semantic meanings, although this model that was presented here looked at prototype theoretic meanings, these are not necessarily probabilistic. they are gradient in a sense, right? They allow for truth values in between 0 and 1, but the truth values don't have to sum up to 1, so they're not necessarily probability, you could say. They're non-normalized probabilities. Actually, if you normalize them, it works exactly the same in these models, but that's a quirk of the models because the normalization will be happening anyway. So there, I think it is very natural to assume, especially in the context of these models, in the context also of recent developments in NLP, that semantic meanings are not necessarily binary and bound to 0 and 1. They can be, so what that means, we'll have to bring the philosophy squad into the picture, I think, how to correctly interpret truth values in between 0 and 1 for a particular model. And the way I would like to do that is not in general, but always to ask, what is the functional role that this numeric value in between 0 and 1 or 0 and 1 plays in the mechanism of this whole model? And that gives you constraints on how you can interpret it or should interpret it, depending on the mechanic role it plays in this model. So for instance, in this quantifier model, I don't think that there is any anything that would pin us down to a specific interpretation that these prototype theoretic semantics are probabilities of any sense. So what that means for other types of the grammar, I would actually not like to commit myself to speaking about syntax, right? I do believe that at least certain pragmatic rules are also not carved in stone, so to speak. I do believe that we see quite quick adaptation to pragmatically aberrant behavior, like over-informative speaker, under-informative speakers in psycholinguistics experiments. So that at least a flexible representation of pragmatic expectations, how my interlocutor will behave, is, I think, very important. I think that's true. We have to model, or we have to assume that people are flexible in what they expect others to do with language. So at some point, I think it's not enough to just assume one grammar and that's it, without any way of changing it and weighing other potential grammars that are close to it. But whether that is probabilistic and at what level that is depends on, I think, the case study you would like to look at.
Okay, thank you, Michal. I'm going to turn now to a couple questions from the chat. So first, Alina Jacheva asks what the psychological assumptions are for probabilistic pragmatic models, the ones you're talking about. So specifically, she's wondering whether we assume that these multiple recursions are happening every time a listener hears an utterance, or that most of it happens during learning, and different meanings are then cached and retrieved depending on the context. How much of this is happening online in the moment?
Excellent question, Alina. Thank you for bringing it up. I don't think that in general conversation, if we are behaving pragmatically on a normal level, they say, enriching a message to its more informative content or its relative content, that we go through any type of deep theory of mind like reasoning. I think that the standard processes, when we are not dealing with intentionally misleading or potentially misleading and uncooperative speakers, etc., are to a certain extent automatized. So my favorite way of thinking about the RSA modeling framework that I have introduced is that, for instance, although we make recourse to the literal interpreter when we describe the speaker rule as being truthful and informative, I don't think that we have to be committed to that being an actual process of imagining that the person I'm talking to is a literal interpreter. It's more something like a rationalization of probably a choice heuristic that we have learned, that we have acquired, and that makes good sense, unless we are faced with aberrant speakers, with malignant speakers, etc. And then similarly for the listeners as well. So there are good arguments for not thinking that listeners can do very complex joint inferences over 27 contextual parameters by fully executing Bayesian reasoning on that high-dimensional space. Nevertheless, these computational level and abstract descriptions that assume this rationalistic framework that I've sketched out here, I think, are explanatory, because even if the actual computations are in some sense amortized or learned or evolved, it still is explanatory to describe their functional rationale. So I don't think that you have to be committed to these processes being cognitively online and real when you do this kind of, let's say, rationalistic back and forth modeling at the computational level.
Thank you. Next question from the chat from Kyo Bach. They ask, I'm curious what kinds of assumptions have been used for defining the alpha parameter, the rational one you use in your hierarchical model. Can you talk a little bit more about that parameter?
I would love to not to have to talk about the alpha parameter, but the alpha parameter is really nasty in some sense. So I'm now speaking loosely here. Okay, it's a softmax parameter. It's a standard mathematical formulation that is used very frequently. I could tell you how you can actually derive it, for instance, from stochastic choice theory, but it is problematic for many different reasons. So one value of alpha equals to 5, can mean something completely different from one model to the next, because it all depends on how the overall structure of your utilities is looking like. So what do we do with these alpha parameters? So normally in Bayesian inference, I would like to not fix them. I would like to keep them free model parameters and put loosely informative priors on plausible values. For instance, that alpha is 0 or even negative is very unlikely, but whether it should be 5 or 5.5 is almost impossible to distinguish or to settle beforehand. So that's also why all the models that I've looked at here basically had rather loose priors over the alpha parameters. The last one actually didn't have any alpha parameter because of the way pragmatic felicity was formalized. But I'm not sure. I hope that settles your question somewhat. Short answer, it's tricky.
Yeah. There's also some recent work out of MIT, Noga Zaslavsky, who's been looking at the behavior of alpha in some of these models. If anyone is interested in some more of the gory details, although it does get quite gory. Okay, so Michal, I wanted to ask you a little bit specifically about the nested Aristotelian case study, and specifically the role of alternatives. Mm-hmm. So we know that the alternatives available can lead to very different predictions from some of these models. So it seems like what alternatives one has available can change the behavior that we might expect to observe. And I'm wondering whether artificially constraining the set of alternatives to those 9 nested Aristotelians could lead to some of the observed grammatically pragmatic behavior. So if I don't have a perfect way of expressing a meaning and I have to spread these meanings around across the possibilities that I do have, could that be driving some of this behavior?
You mean in particular that the fact that the global intentions model was preferred? You think exactly. That this could have been an artifact of the fact that we only looked at 7 world states and these 9 sentences?
Yeah, it's not an accusation. It really is a question.
Good, of course, yeah, be critical. So I'm not so sure, actually. If anything, I would say is I would rather accept that criticism like the other way around. If the vanilla RSA model had come up the best, then I would much rather be inclined to say, okay, maybe that's just an artifact of just looking at this very constrained set. So the fact that, but okay, if we look more closely at this model and the reason why the global intentions model was better, we actually see that for some of the cases, it's actually not all of the alien strength, some of the water case that is maximally driving this result, but it's the sum of the alien strength, some of the water case, for which there are multiple readings made available by the grammatical model, including one that uses a top-level parse, which gives that sentence a rather specific reading. And indeed, for that reading seems to be used, so to speak, by participants. So yeah, I'm not sure what that means about this line of criticism. Whether this, I think I have to throw my hands in the air, Greg, and say it's fair criticism. It's criticism that should be voiced, and it's absolutely clear that this is a toy experiment, like with an artificially restricted domain. And I do completely agree that follow-up research should look at more complex cases. But this question of potential alternatives that figure into pragmatic interpretation is also very nasty. And the bigger you go, the more naturalistic you go, the more that problem looms. So I can say a bit of what I already know and did beyond what I just presented. There are also, of course, different versions of exhaustivity operators, and the differences hinge on which alternatives you take into account. So there are actually in a model like this that I presented here, two types of alternatives. There are let's say the RSA style, the pragmatic alternatives, and there are the grammatical alternatives. And they don't need to be the same. And then when you think about back and forth reasoning, the alternatives that a speaker has in mind in one world state don't need to be the same as the alternatives that a speaker has to have in mind in another world state. And then it just completely explodes in terms of computational complexity also, what proper reasoning about alternatives could be. I hope that the experimental theoretical pragmatics community will find a way of harnessing this problem of alternative states and or alternative forms. And my best guess is that potentially also computational linguistic applications could help, like maybe looking at embedding spaces or something like that. But I think that's a very important and very pressing open problem.
Thank you. So related to that then, in terms of the actual theory specification for that nested Aristotelian study again, so given that it seems like the global intentions model is outperforming the other models because of specific interpretations, maybe not the full range that it's generating, have you considered looking at yet more intermediate models that might selectively target those interpretations where that model is outperforming the others?
No, we haven't, because first of all, well, I think the way we went about this is we just wanted to put a new idea out there. It at least at the time we did this, it felt already bold enough to say, look, we're going to put pragmatics back on top of the grammatical generation of readings, because the development so far was, there was pragmatics, and then we realized, oh no, there's much more that we need. Maybe we need a grammatical mechanism that generates these readings, but then they are not selected for. And then this paper is now saying, okay, let's use pragmatics again on top to try to sort this out. And that's already quite, I'm not sure. It was enough of a step, like saying minimally published unit or something like that, so that I have to think about what that means, etc. But in carving out those four models specifically, we were also guided by conceptual concerns. So I don't think that, I think that not any subset from those 8 parsers that you could think of makes for a plausible model. More concretely, the lexical uncertainty model that I introduced, that was introduced by Chris Potts and colleagues, and the lexical intentions model, which are minimally different because the one allows 2 more parsers, they're conceptually quite different. In the one case, the speaker is ambiguity aware and chooses the intended reading, and in the other, the speaker, at least in terms of the model, just has this one fixed mental lexical entry, and that's it. So there's also conceptual, so in other words, it's not just specifying which subset of readings are available, but also giving them a good and plausible conceptual role in the pragmatics model then. So that's also why I cannot think of, I couldn't think of any other intermediate model that is conceptually plausible and has a good mechanistic realization in the framework that we adopted.
At the risk of getting too far into the weeds with that, is it the case, I don't remember, with the global model that you have the option of the matrix exhaust?
Yeah.
And that's what's doing the work with the sum for you. Yeah, interesting. So this could be a case where, in addition to these methods helping to adjudicate between theories that already exist, maybe then feeding back into the development of theory and exploring that possibility space even more, again, with these conceptual considerations that you mentioned, constraining that.
Yeah.
I'm wondering, kind of shifting gears a little bit and looking more toward the future, what you think the next questions are that might be ripe for this sort of theory-driven statistical modeling. Are there things that come to mind as particularly well-suited or in need of an approach like this?
Other people are doing this, right? It's not just me, and I think that's happening at many different fronts. So I can just maybe topic drop and maybe name drop a few things, but I think that in general, work that looks at the use of language to communicate generalizations, like generics, habituals, causal structures, so therefore also conditionals, is very important also. And the reason I feel that is because I think that is where a lot of knowledge is transferred, and because having a better grasp of also the pragmatics of, let's say, causal explanation or causal, transmission of causal information, for instance, can be also helpful in applied domains, obviously. Yet another area where I think much more could be done is in terms of pragmatics of questions and the pragmatics of answers to explicit or implicit questions. So generally reasoning about in what way a statement was relevant, which QED it might have addressed. But it branches out, of course. And I think maybe that's one final thing to say. I think that this computational driven work is particularly useful, potentially useful, because especially if you use probabilities, it's also easy to, it's not as if it's just plug and play, but it's easier to combine with modern NLP applications that also use numeric representations, sometimes even probabilities, depending on where you look.
Okay, great. So I think that's our time for today. So I want to thank you, Michael, on behalf of Aberlin, and thanks to all of you out there watching, either now or asynchronously. And Michael, if you have any parting words for us, please share them.
Yeah, I might just want to wrap up and say once more, I think enlarging a methodological toolbox is a potentially good idea. That explicit theory-driven statistical modeling can particularly help experimental semantics and pragmatics and maybe other fields in theoretical linguistics to achieve more clarity on what we're measuring, to be able to actually specify what we're measuring, to compare different theoretically interesting approaches really directly, on large data sets, so not just focusing on one or two choice selections of data points. And I think that this is not necessarily something that goes against doing theoretical work or doing experimental work in another way. Because if you look at psychology, you have mathematical psychology as an established branch. You have within psycholinguistics, you have established research in computational psycholinguistics, which similarly tries to make rather concrete models, eye gaze, hand movements, etc. So I would hope that also theoretically minded linguists would help set up a sub-community with some fruitful exchange between, let's say, standard experimental methods, theoretical work, and maybe as a third component, this computational theory-driven statistical modeling. Thank you very much for your